Hey! Welcome to my part two of muscle anatomy. Um, I tried to make it short, but this is by nature a verbose subject. If you don't know what that means, just look it up. Um, Verbose. Anyway, all right. So, what I didn't get to was the nature and mechanics behind muscle contraction itself for both for all of skeletal, cardiac, and smooth. I hope to get to that in this video. I also hope to finish up our my review of what a muscle cell actually looks like. So I'm going to do that first, all right? So you remember how each you remember how each unit of myofibrils is called a sarcomere, and within each sarcomere are all of these myofibrils, and within all of these myofibrils are myosin and actin, allowing it to change shape through their individual motions, which I discussed in the last video. I mentioned a bag called the sarcoplasmic reticulum. Remember, sarco is flesh, or in this case, muscle. Plasm is, well, plasma. It's the jelly in cells. And reticulum means it retains something. It's holding something. So in this case, it's holding calcium. And when a nerve like this one is tells the muscle to contract, it basically goes straight to the sarcoplasmic reticulum, among other things, and it tells it to release all the calcium it's holding, because it's a reticulum, it's a bag, it's holding calcium in this case, and the calcium floods the sarcomere, allowing for the tropomyosin ropes to let go of those actin filaments, the thin filaments I talked about earlier, etc. So that the myosin can attach to the troponin and move, etc. You'll notice that there are these little things are called, well, you know what a mitochondria is. The powerhouse a mitochondria is. It's the powerhouse of the cell. You'll notice in a in a muscle cell there are a lot of mitochondria, like all along each myofibril and all around each one. And then and the sarcolemma is the cytoplasm, basically, of the muscle cell. It actually goes over the entire cell, but it's been pulled back in this demonstration to show you what it looks like underneath. Sarcolemma is the gel holding everything up and giving it support, and then you'll notice on other displays of muscle cells, there's a whole lot of these dark spots, which are nuclei of the muscle cell, all along each muscle cell, which goes the entire length of a muscle. These nuclei are needed, of course, for maintenance purposes, and replacement and growth of muscle, so that it has the access to the DNA recipes for the proteins it needs. Because remember, DNA is just codes for proteins that do specific things. And at this point, since you're watching this and you're probably in high school, and if you're in high school, most of your DNA is probably no longer relevant, because a lot of your DNA is used in making you. But in any case, so yeah, that's the muscle cell, and that's the sarcoplasmic reticulum, sarcolemma. The sarcolemma, remember, flesh, which is muscle, and lemma, which is I don't know, but I'm pretty no. Yeah, it's lemma in medicinal terms, medicine. It's just talking about the suffix lemma. The part of the word lemma is just talking about the plasma, the gel inside of your cells, holding it up and together. So yeah, let's start with skeletal muscle contraction because that's the hardest, and therefore after we get through that, it'll be easier. And other things. So let's start at the neuromuscular junction, or the NMJ, as it may be referred to on your test. It will be if you go to my school, actually. So those of you who know stuff about a synaptic gap in general know that it's normally between two nerves, and they're communicating back and forth. Of course, a muscle doesn't talk back to a nerve. Nerves talk to nerves. So right here, this is a one-way synapse where a neuron will be talking to a muscle. One moment. Anyway, so I don't know what this T tubule is. Oh, I don't know. Anyway, so right here is a depiction of the join between a neuron, a nerve, and a muscle. So the way a synapse works is so neurotransmitters, nerve message carriers, neurotransmitters, neuron or nerve, and transmitter or message carrier neurotransmitters are tiny molecules, or relatively tiny molecules that are in this axon terminal, or the terminal button, or the axon button, whatever you want to call it. And when an impulse goes down the axon of a nerve, down the long part, it ends up at this terminal. And in these bubbles are all of those neurotransmitters. And so when the impulse fires, these bubbles float out to the ends, are pushed out to the ends, pop, and release the neurotransmitters into the other nerve, or in this case, into a muscle. Or in this case, into a muscle. In muscles, they fire acetylcholine, which is the neurotransmitter that makes you move. You've got a lot of it in your body. So these neurotransmitters are acetylcholine, and these little bubbles are called vesicles. Vesicles. You can replay that again if you need it. And you can look it up. These vesicles containing the neurotransmitters spray this end of the synapse, and it activates all the chain of events that lead to your muscle contracting. Of course, this is all very, 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 very fast, but to explain it step by step is to reduce it in time drastically, or a lot. And so they stimulate the muscle, and all these things happen. You don't need to know most of these for most high school tests. But in essence, they allow they signal the sarcoplasmic reticulum to release all that calcium, to move the tropomyosin out of the way, so that these little myosin heads can latch onto the troponin on these actin filaments and detach and reattach and basically walk up, contracting the muscle. You remember all of these mitochondria? They're constantly making and producing all of this ATP so that there's a mitochondria, I think, next to each individual myofibril somewhere. See, and each bundle of sarcomeres, which is a myofibril. So basically, acetylcholine triggers the endoplasmic reticulum to let go, to release all of the chlorine, which moves the troponin out of the way, so that the ATP, which there is a whole lot of, can encourage the myosin heads to move. And remember, each detachment, movement, and reattachment, each of those things requires an ATP molecule for it to happen, which is why there's all of these mitochondria over here. So, again, all of this is happening so fast that it can go like this, but this is one nerve impulse going back and forth with this muscle and this muscle over and over and over and over and over and over and over. Anyway, so yeah, I think that's it. Yeah, so these little extensions and where it gets close to the neurons, it's called dendrites, where it's receptive to these neurotransmitters, and then this is the axon, and these are the vesicles, etc. This area is called the motor end plate. See, right below the axon button. And so yeah, I talked about vesicles, neurotransmitter, and acetylcholine. So in your muscles, there's each bundle of muscle fibers. Each muscle has lots of neurons going all the length of it, and each of those neurons activates one motor unit, that's one area, and only that terminal end of a neuron will be affecting it. That's a motor. That's a motor unit. So you remember how some muscles are classified by shape? There are a few main shapes. Pennate, like a feather. Multipennate, like lots of feathers. So there's you remember how I talked about my you remember how I talked about my teacher doing a whole bunch of this? So I'm going to move this to a new tab. And while that's loading, I just feel the need to remind you, I'm not good at this yet, and I really would appreciate your feedback. So what my teacher did was he also, in addition to that bunch of stuff that's over here, he also uses, he didn't make this, mind you. No, wait, he did make this. He made a PowerPoint right here. He made a PowerPoint with everything that we need not everything, but most of the things we need to know for the test. But then again, at the end of this is meant to be displayed, and at the end of each slideshow, there's sometimes a picture that goes over everything else, so it can get hard to work with. Ugh. So this is what I'll probably be using for that's what I'll probably be using for next video. I think that was the wrong one. Sorry. I don't have the energy to edit this out right now, so if you watch it before it's been edited, if it gets edited, I'm sorry for wasting that little bit of your time. So yeah. All right, yeah. Okay, so this is it talking about the sliding filament theory. We talked about how the thing. I don't even remember where I was. Yes, I do. So motor units. Yes. So in a pennate. I'm so sorry for wasting your time like this. In a pennate muscle. You know, I would really appreciate if you watched my other videos. They're not this boring. In a pennate muscle, it looks like a feather, and each branch of one of those feathers would be a motor unit, and each motor unit is affected by one neuron end. Remember, a neuron can have hundreds of different ends. See, pennate. These are unipennate, bipennate, multipennate. So each of these little bundles right here, that's this from here to here might be one motor unit. All of these bits of the cell will contract together. However, down here it might not if you're just spasming, but most of the time they'll all contract together if your muscles are working right. So yeah, just a little looking at the names of the shapes. That's important. Remember, triangular looks like a triangle. Fusiform, it's like a piece of candy closed at the ends. Ways to name muscles is part of the shape, so this is something you might want to think about. Parallel is like fusiform, but not closed at the ends. And circular, obviously, it's a circle with a detachment point right here. Unipennate looks like one side of the feather. Bipennate looks like two sides of the feather. And multipennate means it looks like a lot of feathers. Anyway, so yeah, it activates the each motor unit is activated by a single neuron end, and they cause the following things to happen. So a nerve impulse goes down, acetylcholine affects the muscle, the impulse enters the sarcoplasmic reticulum and T tubules, that's right here, and right here, this blue stuff that's not light blue. I'm so sorry for wasting your time like this. I wouldn't blame you if you had music going on in the background. It goes and stimulates the release of calcium, and they remove the tropomyosin, which allows the myosin heads to connect to the troponin and move because of all the atmospheric ATP, the ATP that's just around in the sarcolemma. It allows it to move and move and move and move. over and over and over again, really fast, actually. And it shortens the sarcomere, and then once your neuron stops firing, the sarcolemma and the T tubules retract all the calcium. They take it back out of the sarcolemma, and the tropomyosin goes back over the actin, and all of the myosin heads let go of are forced to let go of the troponin because they can't access anymore, and the sarcomere goes back to how it belongs, relaxed. But remember, all of this happens really, really fast because it's all on a molecular level, and everything has such a short distance to go. And see how even this illustrates my point exactly. Anyway, so that's skeletal muscle. That's the ones attached to bones. Smooth muscle, like the stuff in your guts and a little bit in your mouth, they're more spindly. So the characteristic of skeletal muscle is is the fact that you can see the differences between all the sarcomeres. It's striated, it's striped like a candy cane. Where remember, candy cane is skeletal or cardiac, whereas smooth muscle cells are more blobby. They're not super striped. They're just kind of wavy, and they don't have a lot of nerves in them. They just kind of activate one another. So a nerve might activate a couple of them, but they'll activate each other. Or wait. So there are two kinds of smooth muscle. Visceral, which is what I was just talking about, is the kind where some muscle fibers will activate other muscle fibers and they'll all convulse, which is visceral is all like that's the main reason of visceral muscles. Unlike skeletal muscle, they don't have chi tubules. They each of these small, very small muscles have only one nucleus, and they only have one connective tissue. So remember how skeletal muscle tissue had all of these layers of wrapping and connective tissue and actual muscle cell? Well, smooth muscle only has one, and it's the endomysium. It's the endomysium. Endomysium. So the visceral I just told you about, they tend to display this rhythmic motion where they go and they go and they go again and again until they're told to stop. Like when you're vomiting. Sorry. And then there's multi-unit, where this smooth muscle cell has these long strands, like, so I don't. Okay, so you probably can't see it super well, but in my iris, an iris is a perfect example of a. I'm sorry, this is probably super loud. Of a multi-unit smooth muscle. It's less well organized than in regular smooth muscle. It's less in sheets and more in like just jangles. See how my iris, or your iris, if you look in the mirror, is just all these jangles going all from one direction to another? Well, they're they're structurally independent of one another, and each of them, they don't activate each other like viscerals. visceral or single unit smooth muscle, they are activated only by neurons, but all of them have so many that they're super influenceable. So it's like, it's really hard to control them consciously. So, yeah. But just like skeletal muscle, they have actin and myosin, and that's how they move. They have all these sarcomeres. They're not super organized like skeletal muscle. It's just all kind of like sheets that tense, or just like rings that, like in your iris, that just close or open, or just it's like this entire mass of flatness suddenly changing shape in a specific way, like your diaphragm, into one shape. It's always the same shape too. Whereas this can go back and forth because it has opposed the agonist and antagonist, and then all the fixation of the fixative muscles and the synergistic muscles, which I told you about before. But they also and they're affected by acetylcholine too, but they're also affected by non-epinephrine, and also a whole bunch of different kinds of hormones, which is why you feel when you are really angry or happy, you might feel it in your guts because there's a lot of smooth muscle there, and they're really, really sensitive to your hormones. So yeah, they activate almost completely the same, except instead of sarcomeres, they're just kind of these lines of myosin and actin going in all of these different directions in visceral, and in multi-unit, they're all going in this same direction in one cell, but all of these cells aren't going in the same direction, like ever, almost rarely.
I don't know how well you can see it,
but I'm hoping you can see it well enough. And they can also be affected by all of these things. They can be affected by your environment, by your lack of oxygen, too much acid in your body, or just too much carbon dioxide, or your hormones. They're super sensitive, which is why your guts are super sensitive, because they're filled to the brim with smooth muscle. And but they're only sensitive to, well, environmental factors. They're not sensitive to each other. Like, I can't feel the food moving in my guts, but I can feel it in my guts when I'm happy or sad or dying of strangulation or blah, 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 embarrassed. Cardiac muscle, which is in your heart. Oh my goodness, I have 2 minutes left. Like, comment, share, and subscribe. Cardiac muscle in your heart, they're almost just like skeletal muscle, except rather than connecting to your skeleton or to connective tissue, which is most of the time cartilage in the case of skeletal muscle, cardiac muscle instead is attached to itself, and these little discs of stuff, of connective tissue. So yeah, feel free to read this, pause this and read this. It'll help you explain it better than I can in half a minute. And you know what? That's the end of the video. If you need to look up terms in anything I just showed you, feel free to look it up. If your goal isn't learning, but to get past the test, if you paid attention, you should do fine. Thanks for watching. Never stop learning. Bye now.